In working this example, we are going to use a specialized bridge network known as a Wheatstone bridge. A Wheatstone bridge is an electrical circuit used to measure an unknown electrical resistance by balancing two legs of a bridge circuit, one leg of which includes the unknown component. The primary benefit of the circuit is its ability to provide extremely accurate measurements. Most electrical meters use a small portion of the current to cause the meter deflection. Although this is extremely small, it does detract from the accuracy of the measurement. In a Wheatstone bridge, the measurement is taken when the meter deflection is zero. Hence, no energy or current is used for the meter deflection. As in this slide, Rx is the fixed unknown resistance to be measured. R1, R2, and R3 are resistors of known resistance, and the resistance of R2 is adjustable. The resistance R2 is adjustable until the bridge is balanced and no current flows through the galvanometer, Vg. At this point, the potential difference between the two midpoints, B and D, will be zero. Therefore, the ratio of the two resistances in the known leg, R1 divided by R2, is equal to the ratio of the resistance in the unknown leg, Rx divided by R3. If the bridge is unbalanced, the direction of the current indicates whether R2 is too high or too low. At the point of balance, R2 divided by R1 will equal Rx divided by R3. Or, rearranging these terms, we can say that Rx is equal to R3 times the quantity R2 divided by R1. Detecting zero current with a galvanometer, Vg, can be done to extremely high precisions. Therefore, if R1 and R2 and R3 are known to a high precision, then Rx can be measured to the same higher precision. Very small changes in Rx will disrupt the balance and are readily detected. Proving these equations is an exercise in itself and worthwhile going through. First, using Kirchhoff's current law to find the currents at junction B, I3 minus Ix plus Ig is equal to 0, and in junction D, I1 minus I2 minus Ig is equal to 0. Then we use Kirchhoff's voltage law around the loop ABDA. So the voltage drop across R3, which is I3R3, minus the voltage drop across Ig times Rg, minus the voltage drop across R1, which is I1R1, is equal to 0. And in the loop BCDB, Ix times Rx minus I2 times R2 plus Ig times Rg is equal to 0. When the bridge is balanced, then Ig is, or the current is 0. The current Ig is 0. So the second set of equations can be written as I3 times R3 equals I1 times R1, and Ix times Rx is equal to I2 times R2. Then we take the first equation and divide it by the second equation, and the resulting equation is rearranged, giving us this. When Ig is equal to 0, I3 is equal to Ix, and I1 is equal to I2. I3 times I2 over I1 times Ix cancel out of the above equation. Rx is now given as Rx is equal to R3 times the quantity R2 divided by R1, which is what we set out to prove. Before closing, I want to let you in on an early Prime Day sale at Jackery Canada solar generators. Simply go to this web address, which will allow you to get in on up to 65% savings. This brings us to the close of this section of the problem and its solution. If you want the full range of problems and their solutions, you can find them by going to my stand store at this web address. And finally, my newest course that I just added, Bridging the Gap Between Theory and the Practical. This course was developed specifically to solve the pain point of those newly introduced to the power industry. Whether you're an engineer, technologist, or electrician, this course is designed to give you a preview of what's ahead of those just leaving the halls of book learning and entering into the electrical power industry.